Hello, Math Geeks. Welcome to Unit 4 and Systems of Linear Equations. You should have two other things with you right now while you're watching this video. You should have the video worksheet, which is a two-sided worksheet, and you should also have the Solving Systems by Graphing foldable note. That's a small booklet with 3 tabs. So if you don't have all that stuff, please gather it now, pause the video, and gather what you need, and then we'll get started. Okay, so in order to talk about systems of linear equations, I'd like to start with a simple idea. I'm thinking of a relationship between two numbers. The two numbers add up to 8. So let's use x to represent the first number, and we'll use y to represent the second number. That way, when we talk about solutions, we can talk about solutions in terms of an ordered pair x, y. So I want you to think of two numbers that add up to 8. You may come up with several examples. You might have come up with 1 and 7, 2 and 6, 3 and 5, 4 and 4, 5 and 3. These are the obvious integer values, but they're not the only values. They're not the only two numbers that would add up to 8. Can you think of others? Here are some less obvious examples when we incorporate negative numbers, decimal numbers, or fractions. In fact, there are an infinite number of ordered pairs that would add up to the number 8. So would it make sense to try to list all of the ordered pairs that would add up to the number 8? Of course not. In algebra, we know that we can represent this relationship with an equation, and then to show all of the solutions to that equation or to that relationship, to that rule, we can graph the equation. So let's do that. I want you to think of an equation that represents this relationship where x and y added together is equal to the number 8. And I think that you can pretty quickly come up with this equation, x plus y equals 8. So let's take a look at the graph. Here I've graphed all of the solutions that we talked about, and I've connected them with a line because it's a linear relationship. And you can see that in between each of these points, there's yet another infinite number of solutions in between any 2 points. So the graph represents the infinite solutions to the equation x plus y equals 8. So if a point is on the line, like 1, 7, that means that those xy values are a solution to the equation x plus y equals 8. So 1 plus 7 equals 8. And 1, 7 is a point on our graph. 8 plus 0 equals 8. And 8, 0 is a point on our graph, and so on and so forth. So let's ramp this up a little bit. I'm thinking of another relationship between two numbers, and these two numbers are equal to each other. If we let x equal the first number again and y equal the second number again, we can represent this solutions to this relationship again as an ordered pair. And if you were to think, it would be pretty easy to come up with some numbers that equal each other, right? Some examples, 1, 1, 2, 2, 3, 3, 4.23, and 4.23. And again, for this relationship, there is an infinite number of solutions. And we can't write them all out, but we can surely come up with an equation that represents this relationship, which is x equals y. And we can show that on a graph to represent the infinite number of solutions. So here on this graph, you can see I've graphed some of the common examples, and then I've drawn a line to show that there is an infinite number of solutions between these solutions and going on toward positive and negative infinity. So again, 1 equals 1, and so the point 1, 1 has been graphed here. 4 equals 4, and so the point 4, 4 has been graphed here. So the graph represents all of the solutions to the rule y equals x. What if I asked you to find the solution that is true for both of these relationships? Find the solution that is true for x plus y equals 8, and also true for y equals x. Well, let's go back and look at our data. So for x plus y equals 8, we have all of these solutions, and we know that if we graph it, we can show the infinite number of solutions for x plus y equals 8. And then we have y equals x. And these are all the solutions, some of the solutions for y equals x. And if we graph y equals x, we can see the infinite number of solutions. So graphically speaking, is there a point that you can identify right away that solves both of these equations? And remember, if an ordered pair is a solution to an equation or to the line, it will be a point on the line. So we're looking for a point that exists on both the orange line and the blue line. Can you find it? Right. It's this point right here. That's the point 4, 4. And you can see that in our list, we actually came up with 4, 4 for both of these because 4 plus 4 satisfies this rule, this equation, this relationship, x plus y equals 8. 4 plus 4, in fact, equals 8. And it also solves this equation, y equals x, because 4 equals 4. Each of these lines shows us for what values of x and y is this equation true. But when we have two equations and we're trying to solve them at the same time, we call that a system of equations. And the solution to a system of two equations is the point that is shared by both of those equations, the solution that is shared by both of those equations. So it must lie on both of the lines. And here we can see it at the point of intersection. So let's get a little bit more formal about what is a system of equations. A system of equations is a collection of two or more equations. We will only be talking about a system of two equations, but it could be more. It could be 3 or 4 or 5 or more. And these equations will have the same set of variables. So in our example, the variables were x and y. These two equations can be considered to be combined with the operator and. So that means, going back to our example here, in our system, we were looking for the point where x plus y equals 8, where that rule is true, where that equation is true, and where x is equal to y, or y is equal to x. So in a system of equations, we can consider the two equations to be joined with the word and. Furthermore, the solution to a system of equations is the set of all points that are solutions to both equations in the system. The set of all points. So in the example that we just showed, there was exactly one point that those equations shared, and that was the solution. Let's look at another example. So here we have two equations already graphed for us. Y equals 3x plus 2 and x minus y equals 2. Now what I want to show you here is that each of these lines has a bunch of, in fact, infinitely many solutions that are solutions to its corresponding equation. Like y equals 3x plus 2 has this solution, this point A, which looks like it's -1, 1, -1, -1. So what I want to show you first is that this point A is a solution to y equals 3x plus 2. But it is not a solution to x minus y equals 2. It doesn't lie on that green line. So it must not be a solution, but let's prove that algebraically. So first I'm going to plug it into y equals 3x plus 2 and prove that it is in fact a solution to this equation. So I'm going to substitute in -1 and -1 for x and y, which will give me -1 equals -3 plus 2, or -1 equals -1. So it checks out that -1, -1 solves this first equation. Does it solve this equation? X minus y equals 2. Let's plug in or substitute -1 and -1 for both x and y. So -1 minus -1 equals 2. Well, that's -1 plus 1 equals 2. -1 plus 1 is actually equal to 0, right? So this does not solve the equation. -1, -1 does not solve the second equation. And that makes sense, right? Because it's not a point on the green line. It is only a point on the red line. So let's try this again with point B. I'd like you to take a moment and identify the ordered pair at point B, and then I would like you to algebraically show that it is in fact a solution to the equation x minus y equals 2 by substituting in the xy values, and then I'd like you to show me that it is not a solution to the line y equals 3x plus 2. So pause the video and do that work, and then come back and check out your answer. Okay, let's see how you did. So you should have figured out that the point B is the ordered pair 3, 1. And let's first substitute that into the first equation, the red equation, y equals 3x plus 2. So we'll substitute in 3 for x and 1 for y. So 1 equals 3 times 3 plus 2. 1 equals 9 plus 2, or 1 equals 11. Not true. All right, let's try again for the green line, or the equation x minus y equals 2. Again, we're substituting in 3 for x and 1 for y. So that's 3 minus 1 equals 2, or 2 equals 2. So that one checks out. So the point B is in fact a solution, as we can see right here on the line. It is a solution to x minus y equals 2, and it is not a solution to y equals 3x plus 2. Okay, let's try that again for point C. So I want you to pause the video, and I would like you to substitute in whatever the ordered pair C is, substitute in those values to both of the equations and see what you come up with. Okay, so the ordered pair C the point C is the ordered pair -2, -4. If we substitute that into the red equation, y equals 3x plus 2, we will get -4 equals 3 times -2 plus 2, or -4 equals -6 plus 2. That's -4 equals -4. So that checks out. It is a solution to the red line, or y equals 3x plus 2. Let's try it for the green line. X minus y equals 2, and we'll substitute in -2 for x minus -4 for y equals 2. So -2 minus a negative is plus a positive equals 2. And -2 plus 4 is in fact 2 equals 2. So that is a solution. The point -2, -4 is also a solution to the second equation, x minus y equals 2. So we have graphically and algebraically shown that the solution to this system of equations is this shared point C, the point of intersection. So will this always be the case when we have a system of equations? Will we always have a solution? Let's take a look at some other examples. So in problem number 5, we're asked to name the solution to the system of equations shown in the graph. And I ask you, how many points does this system share? It's pretty easy to see that there is only one point that both of these red and green lines share. And that's the point where they intersect, right? That's the point -2, -2. That's clearly the shared point between these two lines. So we have one solution for this system of equations. Let's look at another one. In problem number 6, we have another red and green line. And I ask you, how many points does this system share? Take a moment and think, how many points do these two lines share? Do they share this point? Well, this point is on the red line, but it is not a point on the green line. So it's a solution to the red line, but not a solution to the system. What about this point? Once again, this point is on the green line, but it's not also on the red line. So it's a solution to the green line, but not a solution to the system. So if these two lines are parallel, which it looks like they are, then we know they will never meet. And therefore, they will share exactly 0 points. So if a solution to a system of equations is the shared points, then this system, if the lines are parallel, would have no solution. And we can represent that using the empty set. But before I'm ready to commit to that, we need to make sure that these lines don't just have similar slopes, but they in fact have the exact same slope and are parallel. So let's put 2x plus 2y equals 4 into slope intercept form. So let's subtract 2x from both sides of this equation. That'll give us 2y equals -2x plus 4. And if I divide both sides by 2, I will have y equals -x plus 2. So you can see that my slope is -1, the same as the slope of my green line. So these lines are in fact parallel. So we are correct in saying that this system of equations has no solution. All right, let's look at our last final example here. We have y minus x equals 5, and that's the red line peeking out from under the green line. And we have 3y equals 3x plus 15, and that's the green line on top of the red line. And we're being asked to name the solution to this system of equations. And I ask you again, how many points does this system share? It's difficult to tell because this is a pretty small graph, but it looks to me like these lines lie exactly on top of each other. So let's think for a moment. If these lines do lie exactly on top of each other, exactly how many points would they share? I want you to pause the video for a moment and think about that. Did you get it? If two lines are lying exactly on top of each other, then they would share every single point on both lines. So since each line has an infinite number of solutions, then these lines would share an infinite number of solutions. And so this system would have infinitely many solutions. But once again, before I'm willing to commit to that, I need to know that these lines not only have the same slope, but also have the same y-intercept, because really they would be the same line, a copy of the same line right on top of each other. So we'll have to put both of these lines in slope-intercept form. So let's start with the red line. Y minus x equals 5. So I'm going to add x to both sides of this equation. That'll give me, the x's cancel out. I'll get y equals x plus 5. All right, for the green line, we have 3y equals 3x plus 15. And I'm going to divide both sides by 3 to get y by itself. So that will leave me with y equals 1x plus 5. So I have y equals x plus 5 and y equals x plus 5. I do, in fact, have the same line lying on top of itself. These are called coinciding lines. You won't need to remember that, but it's good to know. Coinciding lines in a system of equations will have infinitely many solutions because they share every single point on both of these lines. So we looked at systems that share 1 point, systems that share no points and have no solution, and systems that share all of their points, infinitely many solutions. Those are the 3 basic types of systems. What I would like you to do at this point is to pause the video and finish worksheet number 1. There are 4 more examples, and then come back here, check and correct your answers, and we've got 1 more thing left to do. Okay, welcome back. Let's take a look at your answers for 8 through 11. Double check. For number 8, we have exactly 1 solution, and that is this point right here at 2, -1. For number 9, we have 2 lines lying right on top of each other, and we really should represent this with another line and arrows to show that we have 2 lines. So this system shares an infinite number of solutions. For number 10, we have 1 solution, and that is the point, -4, +2. And finally, for number 11, we have two parallel lines, and we know that those lines will never meet, and therefore the system has no solutions.